Hello, everyone. I'm Micah. I'm the host for today's talk on the Tartan Planning series. It is my pleasure today to introduce Amanda Prorok. Amanda is a professor of collective intelligence and robotics in the Department of Computer Science and Technology at the University of Cambridge and a fellow of Pembroke College. Before that, she was a postdoc in the GRASP lab at UPenn, and Amanda did her PhD at EPFL in Switzerland. Amanda has been honored to receive numerous research awards, including an ERC starting grant, an Amazon Research Award, the EPSRC New Investigator Award, the Isaac Newton Trust Early Career Award, and several Best Paper Awards. And her PhD thesis was awarded the ABB Prize for the best thesis at EPFL in computer science. Amanda is also an associate editor for the Autonomous Robots Journal and chair of the 2021 IEEE International Symposium on Multi-Robot and Multi-Agent Systems. Today, Amanda will be talking about methods for learning cooperative policies for multi-agent and multi-robot systems using tools such as graph neural networks. And I'm really excited to hear more. So Amanda, I would like to welcome you to the floor. Please take it away.
Thank you very much, Mika, for the kind introduction. It's a pleasure to be talking today at the Tartan Planning series. Right, so today I'm going to be talking a little bit about the work that we've been doing in my lab on learning cooperative policies for multi-agent and multi-robot systems. And I really like to begin with this little movie here that shows us that really describes the beauty of collective intelligence and collective decision making. So the adjectives that I commonly or typically see when I see this movie are: this is elegant, it's robust, it's flexible, it's really adaptive. And it just seems to me that we still have a lot to learn from how collective intelligence is emergent and executes itself in nature. So it's definitely beautiful. And so this is how we take these systems into the engineering domain and try to learn from them and do useful things with them. So collective intelligence is definitely beautiful and might teach us a few practical things, but multi-robot teams are actually practical and have already been put to use to many hard problems in the private sector as well. So here are a couple of examples. So we see on the first row a lot of multi-robot applications that we know function and exist already to a large extent broadly worldwide. And these include the successful examples of logistics, transport, and agriculture. But automation has also been shown to be very promising out in the wild in less structured environments. And we know that where various groups are working on problems of environmental monitoring, surveillance in difficult areas, even construction, and thinking about deploying these kinds of solutions to very harsh environments such as space. And so the key point that I want to make here with this slide is that whether it's through simple coordination or more sophisticated forms of collaboration, a lot of systems just simply perform better when there's several robots taking part in the task. And so at my lab, we're interested in figuring out how to get these robots to work together better and more efficiently. So I like to think about collective systems with respect to this categorization into three different categories. So there is coordination, cooperation, and collaboration. And this categorization also would inform us about how we might approach finding different types of algorithmic solutions to the respective subproblems. So on the left, we start with coordination, and we look at problems such as multi-robot coverage, whereby we're looking at sublinear gains in the number of robots. And robots are commonly trying to coordinate with respect to one higher order goal. In the middle, we look at cooperation, where robots might have local goals as well as higher order goals. And we might only have or be gaining super additive benefits with respect to the number of robots as we add robots to the system. And we might be depending on threshold effects. So in a coverage example, as I'm depicting that little image there, you only have connectivity from target to source when sufficient robots actually create a communication pathway from target to source. And so these threshold effects might hold. And so this is cooperation, because robots get together because it's partially in their interest, but not wholly. And collaboration on the right really involves heterogeneous agents, so agents that are complementary in some form or another. And performance definitely improves linearly, superlinearly there. as a function of the number of species. So as a function of the number of different kinds of robots that we have in our system. So a simple example here would be to consider the combination of ground robots with aerial robots, where the different robot types bring in different vantage points, and you might be considering teams of these different kinds of robots to map an area and provide a richer representation of the volume, say, that we're trying to map and represent. So these are the three C's. So why is it that that solving the three C's is so hard? So we're interested in designing practical methods for effective collective multi-robot systems. And it's difficult. So as we start thinking about why it's hard, well, there are several things that come to mind. It's difficult because, first of all, if we look at these problems from a centralized, fully observable perspective, a lot of the problems tend to be proven to hard. So NP hard, NP complete, there are hardness results that tell us that these solutions don't scale that well as a function of the number of robots that we introduce into the systems. So that's number one. So number two, we might say, okay, well, let's reduce full observability. Let's decentralize the systems. Let's make them partially observable. Well, if we decentralize our systems, we still want them to collaborate or coordinate. So we need communication between the robots. And then the question that arises is, well, who are we going to be talking to? What are we going to be talking about? And when are we going to be talking? So the question of how to generate communication policies that are amenable to the downstream tasks is the one that's prevalent in the second pillar. And the third pillar is, well, we then design solutions or devise solutions that maybe solve number one and number two, but as we then transition our systems to the real world, we face the need for robustness because the real world is noisy. There are delays that happen, there are faults that happen, and sometimes not all robots behave as we expect them to behave. And so we need to be able to accommodate all these various artifacts and disruptions in a way so that our robots still remain performant with respect to their higher order goal. And so these are the three challenges that we have, and there have been a number of first principles based approaches that tackle them either wholly or partially. But what I really want to focus on in my talk today, and this is really what my lab has been focusing a lot on in the last few years, is thinking about how we might use data-driven approaches to solve these three different problems, or these three different kind of key challenges. And so the way that we go about this is by posing this kind of overarching question, which is, can robots somehow learn to coordinate? And the research agenda here is really fueled by this simple insight that robot relationships can be represented by graphs. And this allows us to exploit the underlying structure that a graph gives us as our inductive bias in machine learning architectures in order to facilitate the learning problem. So ultimately, what we want to do is we want the agents to be able to learn what to communicate and how to make local decisions based on these messages that they're receiving from other agents in their systems. Okay, so this is kind of the overarching research agenda. So what was the initial idea? So the initial idea goes as following. The premise is in the way we started tackling this idea of using data-driven solutions to solving multi-agent problems, is that success follows from starting with simple problems and using them as examples to approach more complex ones. So if we look at that at the x-axis here, we're looking at the ways in which small problems become bigger and more complicated. And the y-axis tells us how much information any given agent might have in a system. So the first box, top left-hand side, is our offline optimal box, which tells us, okay, this is a system which is potentially composed of just a handful of agents. They have full information or near to full information. Perhaps it's fully observable. It's small scale. And for those kind of systems, we know that we have optimal solutions, so provably optimal solutions that are definitely computationally feasible in an offline setting in the small regime, in the small scale regime. Okay. So we have really great solvers for this. As we move onto the right, we go to offline proximal solutions where we're looking at really, really, really big systems. We know that there are certain heuristics that simply perform really, really well. So we have offline proximal solvers. One example would be solvers for the TSB, which we know perform extremely well and are very close to optimal. So there are some offline solutions we can run. They take maybe some time to run, but they perform well in large scale. So now going down my y-axis in the small agent number regime, we're looking at systems that are small but have very partial information. And for those kinds of systems, we know that there's theory on partially observable market decision processes, which are also hard to learn, but that we know function very well and provably to optimality within the small agent number regime. Now, as we move to the right into this lower right-hand side box where we're looking at online and scalable systems, that's where things start to become a little tricky, because we have few solutions that are really able and capable of making decisions quickly in real time as a function of real-time incoming information in the large-scale regime. And that's really what we want to do by leveraging machine learning methods. And so the idea here is, well, we're going to start by trying to glean ideas and information from these three gray boxes here, from solvers we know exist and we know perform well. And we're going to try to generalize the insights we gained from those solvers to perform well in this last remaining, across the last remaining frontier that we have, which is the online scalable regime. And we're going to really start by thinking about, well, what can imitation learning do for us if we're going to try and tackle the problem in this particular way? And so we came up with our first case study. So the first problem we wanted to tackle, which we thought was amenable to answering this question. So the question is, well, can we use data-driven methods? Do graph topologies lend themselves as the right inductive bias? And can we use imitation learning? And so the problem that we selected as our first kind of scenario was the problem of multi-agent pathfinding for two main reasons. Well, the first reason was it's an NP-hard problem, so it's hard and it doesn't scale well as we move it to very, very large systems. And the second reason we were interested in working with this is because in the small agent number regime, we have solvers that can solve it for us really well, and we will be able to benchmark our data-driven solutions and see how well we're really doing as we start moving away from what our optimal solvers can do. And so what we're going to try to do here is we're going to try to solve the multi-agent pathfinding problem by automatically synthesizing local communication and decision-making policies that run locally on board agents for this hard problem. Okay? So this is how we set up the problem. So our goal here is to derive a local policy, one that runs on any given individual agent, based on observations that are coming in from a local communications neighborhood and that are coming in because the agent can see it within its field of view, and communications that are coming in because the agent can talk to its neighbors, right? So you can see this depicted on this little image that I have here. So if we focus on agent number 4, it's talking to 3 other agents, and it can see everything that's within this green box, which represents its local field of view. It has no global information. It doesn't even know its absolute position, and it only has a direction towards its goal position. So we only have relative direction to the goal. So what we want to do with this is, well, hopefully we're able to synthesize these local agent policies that allow them to move towards their goal positions from specified start positions. And hopefully we're going to be approaching the same levels of performance as we would get in centralized expert solvers, okay? So those that we know are optimal. Yet, of course, we're hoping to scale more gracefully as we increase the number of agents, right? So how do we set up our communications pipeline? So this is the way our system looks. So we're taking in a given agent. We're operating in this particular scenario with a bird's eye view. So an agent has this small surrounding field which it can see. What it sees is going to be pre-processed by a network. In this case, a convolutional neural net, and that pre-processing unit will output a feature vector that is then fed into our GNN, which is a graph neural network that produces an embedding that is essentially our communicated feature. And this GNN, what it's doing for us is it's basically emulating the communication by computing how information is sent and received amongst agents. That output is then fed into a sequence of fully connected layers, so our policy head, if you will, and the robot's motion decision is then the result of a final softmax activation layer in this case, over a discrete set of motion primitives, right? So if we consider a discrete case where we have up, right, left, up, down, left, and right, or stay still, we're considering an essentially a classification problem where the agent has to decide between these 5 different actions, okay? So I'm going to introduce a bit of notation that will describe in a little bit more detail what the graph neural network is actually doing for us here, because that's really the focus and the novelty of this whole pipeline, okay? So the specific mathematical notation I'm using here actually stems from a particular variant of graph neural networks, which is known as graph convolutional neural networks. And I'm using this because it's a very pure way of writing down the graph neural networks. So we begin by looking at it from a centralized perspective, where if we focus on the first equation, we know that S is our adjacency matrix, and we know what these adjacencies are because we have a centralized perspective. X is a matrix that gathers the observations from all agents. And this first equation then basically is telling us how an agent I aggregates the information that is being sent to it over a number of capital K communication hops. The second equation then parametrizes this message aggregation by multiplying it, the observations with the matrix H, and H is our learnable parameter, okay? So H is basically what we want to learn through our machine learning pipeline here. And if we have multiple hops in our system, so if we're not only communicating to our 1-hop neighbor, but we also communicate to our 2-hop neighbor, then we have a bank of these matrices, and we're learning several of these matrices H. So H sub K would be, K is indexing our hop count here. And so G is our short way of writing down what our communication function basically boils down to. It's parameterized by theta sub 2, and theta sub 2 is equivalent to our bank of H matrices. So then, of course, we have to remember that we also have our CNN and our MLP. So those are our pre-processing and post-processing units. And we're going to learn the parameters of those 2 units in an end-to-end manner. So theta 1, theta 2, and theta 3 are going to be all learned jointly. And so we formalize this loss function within our imitation learning setup to minimize basically the loss between what our network is predicting and a expert solver, which we are given because we know how to solve the multi-agent pathfinding problem. And we're going to be minimizing the cross-entropy loss in this given scenario, okay? Because we're, again, just considering discrete actions. So this is the centralized formulation, and we can very elegantly use the centralized formulation for training the system, because at train time, we can assume that any type of information is given to us. Yet at execution time, we need to convince ourselves that the policies that we synthesize here are run on local decision-making, on agents locally running in their own independent decision-making policies with only the input of what they see and what the other agents are telling them. And so that's what I want to go through next. And I want to convince you that we can train these systems in those ways and leverage our whole learned parameter pipelines in a decentralized architecture. So this is how our architecture presents itself if we look at it from a decentralized perspective. So if we look at agent B here, what is going on there is agent B is making a local observation. So if we separate its local observation into 3 separate channels, so one for the agents it's seeing, one for the obstacles it's seeing, and one for its goal projection, we can process this through a multi-channel CNN. That then produces a feature vector, which we denote as X sub B. And that feature vector is what agent B is going to be sending to all of its neighboring robots, so robots that are within its communication range. So agent A will receive this feature vector from agent B. It'll receive the same kind of feature vector from agent C, and it will also be computing its own feature vector, X sub A. So now let's look at what agent A does with all these feature vectors. Well, what agent A does is it simply uses the parameters that we trained previously in our centralized training paradigm that correspond to our GNN. And you'll recall that what our GNN was doing, well, it was training these matrices H, sub-indexed here by the communication hop count. So at hop 0, we're looking at only agent A, so it will multiply it will feed its own, it will multiply X sub A with H sub 0. That will produce a new feature embedding. And we'll be doing the same thing for hops 1 to hops 2 and so on and so forth, in order to process all the incoming information over the different communication hops that we're considering here. And so the trick is that we're aggregating X sub B and X sub C prior to multiplying it with H sub 1, because we have invariance with respect to the size, the dimensionality of the features that are being multiplied with these matrices, right? And so that's where we're independent to the size of our communication neighborhoods, because obviously we don't know what that looks like at runtime. So this is the elegant part of this framework. And so we're aggregating and multiplying and aggregating and then multiplying. And when we've gone through all of our communication hops, we then pass all of this through a nonlinearity. This gives us our X sub A prime. That is then fed into our policy head, and that then outputs our final decision, which corresponds to my action, which is whether I want to move up, down, left, or right. And so I hope at this point you're convinced that, yes, we can train these parameters in a centralized way, but at runtime, it's fully decentralized. And I'm operating solely based on local information. So with this, I'm now going to show you what this system actually can do for us. So on the left-hand side of this little movie, what I'm showing you here is a movie of the expert solver that we use to generate our data for us. So this is CBS. And on the right-hand side, we're actually using our system. So local policies running on every single one of these agents in a decentralized way. And so a lot is going on in this movie here, but what you can see qualitatively is that left and right, they seem to be doing roughly the same thing, and they finish at roughly the same time. And this is a good thing, because it means that although our solver is fully decentralized with only partial observability and information from what it's getting through its neighbors, it's acting pretty optimally. So it's doing what an expert solver would do, despite the fact that expert solvers are planning everything a priori offline with full information. Okay. And so what you can also see in the movie on the right is, so we zoom in on one of the robots and we show it's which other robots it's communicating with as it kind of moves down the scenario, the environment to its destination. And you can see the different communications that it's executing with its neighbors. Okay, so this is a qualitative representation of what our multi-agent policies can do. We show here that it scales quite nicely up to 40 agents, and then we look at it from a quantitative perspective, because what we're interested in is, well, what is the success rate? Do we solve all of the scenarios that we give our systems? And second, we're also interested in well, how good are we actually solving it with respect to an optimal solver? And we can compute this loss in performance because we have optimal solvers, and especially within the small agent number regime. So we're considering systems here of up to 12 robots. In these two plots, we know that we can compute the optimal solutions, and hence we know exactly what we could be doing in the best of cases, right? And so the good news is, on the left-hand side, you can see that as we increase communication hop counts, we're achieving extremely good performance. So we're at a success rate of nearly 100%. And I just want to note here that the metric that we're using to compute success rate is actually very strict. So if we have a system of 10, 20, 30, 40 robots, we only have 100% success if every single one of the robots reaches its goal position. So it's a complete system, or the solution is complete. If any one of the N robots does not reach its goal, this is a negative result and counts as A0 essentially with respect to our success rate statistic. So this is great. So we have systems that show that they can pretty reliably almost always succeed and solve their problems. And this is especially great because we can contrast it with other decentralized approaches. So a discrete version of reciprocal collision avoidance algorithms. And we can see as those increase in size, they deteriorate in terms of success rates. So decentralized reactive type solvers aren't able to solve the same instances that our solver is able to get through. And in the flow time side of things, we also see that we're doing pretty well. So our in the best of cases for hop counts of 2 and 3, we have a flow time increase in the very low digits, so around 1%. And so the take-home message here is really, well, performance looks like it's really good, but what's what's especially interesting to us is that we're no longer, with our decentralized policy, we're actually no longer dependent from a computational standpoint on the number of robots, because we're running it so each robot is making its decision on its own. And so we can scale these systems arbitrarily. And so that's really the neat side of things to us. So then we got on to the next kind of stage of this project, and we thought, well, we're not really scaling our systems a lot yet. In that paper there, we only looked at systems of up to 40 robots. And so we were thinking about, well, what happens if we start running these on systems of hundreds or even thousands of robots? Does it still work? And what we found was that, well, if you start cluttering your environments with many, many, many different robots, the robots have to start learning which other robots' messages do they actually have to pay attention to, so that they're extracting meaningful information from all the information that's incoming. And to make these systems work, what we did in our architecture was add a simple additional matrix that would allow the robots to learn which other robots they needed to pay attention to in order to achieve good performance. So what we then did was, in addition to learning the graph neural network weights, was also learn attention weights, which were a function of ego as well as incoming information. And essentially what we're doing here is learning a pattern of when to pay attention to which communication partner. So we trained this slightly augmented system, and we looked and compared it to the vanilla GNN, and we observed that indeed, as we scale our systems, so we train them on very small systems. So we train them on only instances of 10 or 20 robots, and then we test them on up to 100x the number of agents. Performance is actually looking really good. So those are the green and the blue lines, whereas performance for the vanilla GNN starts to drop down quite significantly when we're not paying attention and not using attention-based mechanisms. So these were a couple of the insights we had as we were studying multi-agent pathfinding. And we started to get excited about all of this, but then we started thinking about, okay, so we're doing all of these things in simulation, and a core part of everything that we're doing is really learning the communications between the robots. But communications in simulation is really different to communications in the real world. And so we took a step back and we thought about, well, before we go any further, let's analyze what we need to do in order to ensure that all the policies that we train in simulation also transfer in a hopefully graceful way to real world scenarios. And so the question that we asked here was, how do we enable zero-shot transfer of GNN-based policies to the real world? And we thought of a new research scenario that we thought would elucidate this question for us better than the multi-agent pathfinding one. So the problem that we came up with is this problem of, you have a robot formation that has to fit through a constriction and reform on the other side. And it's really interesting for answering this question, because it's a make or break type scenario, right? So the robots here, they don't know anything about each other, so they can't observe each other relatively. They rely 100% on communications in order to glean some information about the state of the other robots, so that they can coordinate to fit through the constriction and reform and regroup with respect to their destinations on the other side. So the pressure is all on the communications to do the right things to enable coordination in this scenario. And that's why we call it a make or break type thing, which hopefully will tell us about whether or not our GNN policies transfer gracefully to the real world. So how did we go about testing this? So this is the setup of what we were going to try to do. So this passageway scenario. And in order to test communications, we came up with essentially a physical ablation analysis, going from the most idealized scenario to the most unstructured, unreliable, real-world scenario that we could think of. And so this transition from idealistic to real world happens across 4 different stages. And I'm just going to walk you through this. So we have in the case scenario number 1, we have basically something that is analogous to what we have in simulation. So we have a centralized system where we have one PC running the policies for all the robots jointly, which which then produces actions for all the robots. These actions are then sent to a router, and the router will then communicate the respective actions to the end agents that are in our system. The agents operate in the real world, but basically the only real component there is, the dynamics, the robots touching the real robot floor and moving in a physical 2D workspace. Okay, but apart from that, everything is dealt with on a centralized computer where everything is synchronized and there are no delays, no communication losses. So our first step in this physical ablation is to say, okay, now we're going to move off board or we're going to relax the synchronicity of our system by running the local policies asynchronously on our PC. So we have a threading mechanism, and these individual policies are then exchanging messages with one another, but it's, on one computer. It's all happening on one computer. And when these individual policies know what they want to communicate, those different actions are sent to the router, and the router commands the robots to do those things, okay? So that's the first relaxation that we perform. Then our second step is saying, okay, we're going to no longer use our centralized computer. So we're moving on to a decentralized off-board regime. We're going to be running the policies on board the robots, but we're still using a router to kind of manage the whole message passing thing, okay? So that's our next relaxation. And the final relaxation is to say, okay, we're getting rid of the router. We now have point-to-point communications hardware on all of our robots. It's an ad hoc network, and the robots are just talking to each other in a total ad hoc point-to-point manner. So no more router, absolutely no infrastructure, and everything's happening in a completely unregulated, unstructured way, and the robots basically communicate the best they can in this ad hoc regime. And so we're going to run our GNN-based policy that we trained in Sim on these 4 different scenarios and study how performance degrades. And so what I'm going to show you here is our results in form of a qualitative visualization. And so what you see here is, as we kind of go through this movie, is the robots executing one of the policies. And the overlay that we represent on that movie is basically the ideal scenario that the ideal positions that the robots should reach with respect to what the ideal simulation-based policy would have predicted the robots to do. Okay? So this is just setting up the problem. So we train these systems in our simulator. The simulator predicts how the robots should be moving. This would be the version. We have a centralized planner. We then run our policies in 2 different modes, centralized or decentralized. When we run it in the centralized mode, in the real world, we're basically having the PC tell the robots what to do. And you can see that visually, they do pretty well with respect to the overlay of the yellow and the blue. And they reach their goal positions quite reliably without too much delay. And then we move on to the decentralized mode, where we no longer are using our centralized computer and everything's in ad hoc. And again, you can see now in a qualitative manner, well, the performance of the robot seems to be very similar to what we had before. And we definitely pass our fail test, which is the robots are able to actually leverage these communication policies that were learned in simulation to perform a difficult task in the real world, despite the fact that all comms is now functioning in a way that would happen in any non-asynchronous real world type setting. So this is good news. We have quantitative plots in the respective paper. And the insight from those is that there is a small performance degradation in terms of how quick the robots are to reach their goals, but this performance degradation is very graceful. And there is still some work to be done. How do we close that gap? But we leave that to future research agendas. So the last project that I want to talk about today is another project where we're looking at what we can do with GNN-based policies in the real world. And so we have this problem that we're really excited about, where we're looking at the scenario where we have a robot that's in an environment, and the robot, in order to to get to a target location or to find a target, where that's the goal of the system. So the robot has to find a target. It doesn't have that information, so it doesn't have a map. It doesn't know where the target is, and the target is definitely hidden behind obstacles. And so in order for the robot to do that, it basically has two options. It can either explore the environment randomly and kind of just find the target, or it can leverage information that is being sent to it through a sensor network, through a visual sensor network that, through its connectivity, through its visual connectivity, can see the target. Okay. So you could even imagine that this robot is completely blind, carrying absolutely no sensors, and it's just essentially, a mobile platform that has to reach a target position, and it hopefully would be able to rely 100% on this visual sensor network that can guide it to the target, because the visual sensor network knows where this target is. Okay. So we set up this physical layout here where we have our lab. We have a setup of visual sensor nodes. So those are the blocks in blue. We have a robot that also has a camera. So it could see the target if it's in line of sight. And we have the target itself, which is that green blob in the middle of our layout. And so what we're going to do here is we're going to try to devise a system that is essentially plug and play, because we're aware of a lot of work in sensor network-based navigation literature where we can do these kinds of things, but they require the sensors to be localized. So the sensors need to know where they are, and they need to be calibrated with respect to each other within an absolute coordinate frame. So we want to get rid of that assumption. So our ideal scenario is you walk into a room with, a bunch of sensors, you just put them down on the floor, you put down your robot, and you just say, you snap go, and you tell the robot, okay, now based on the information that these sensors are telling you, go find the target. So nobody's localized, nobody's calibrated, nobody knows where they are, and yet somehow the robot is going to be able to navigate to the target. And so this is the kind of thing that graph neural networks excel at, because they excel at aggregating information across neighborhoods and distill this information into something that is useful to a downstream policy. Okay. And so in this case, our downstream policy is going to be, the robot that has to reach the target. And what our visual sensor network is going to do here is it's going to learn to aggregate this information. So this visual information that the sensors collaboratively are seeing into into a piece of information that is useful to the robot. So how do we train this system? So in our training pipeline, what we do is we consider an image feature extractor. So that's our first bit. So we have these sensors that they have omnidirectional vision. So those are the individual sensor nodes. They first process this omnidirectional input through a feature extractor. This then goes through a feature aggregator, which is our GNN, and it functions much in a similar way as to what I described to you before in this talk. So it's aggregating these incoming features that are coming in across the sensor network, and that is then fed into a post-processing unit. That's our MLP, which then feeds a final encoding into an MLP for a stochastic action policy, which tells the robot in which direction it should head. That hopefully leads it to its target. Okay? So this is basically an end-to-end visual navigation pipeline. So how do we train the system? So we have a cost function where we chain our three machine learning components together. So our feature extractor, our feature aggregator, and our post-processing unit. The input here is basically our observation. So what are the sensors seeing? And we're minimizing a loss that is given to us by this, what we call relative advantage, which is telling us essentially what the cost to go is for a robot over a discrete set of directions that a robot essentially can move in. So the set of k discrete directions essentially corresponds to a discrete set of robot motion primitives, if you will. And so we're going to be predicting the relative cost to go for every one of these discrete directions, and the robot will then, at action time, will select one of these discrete directions and move into that direction. So this is our cost function. It's essentially an imitation learning based cost function because we're assuming that these cost to go functions are given to us, these labels are given to us through some expert planner at train time, for which we have many possible options. And we then use this data set to train our system, producing our final set of modules that gives us our policy. Now, what's important here is the small detail that we actually train the system in simulation first, okay? Because simulation is much more efficient for training policies, especially if we have to feed a lot of different types of observations to the policy for it to learn how to deal with all the various types of observations it could encounter within this given environment. So what you see here is a flattened omnidirectional image taken in the simulator that we use, WebOts. Now, what we actually want to do is we want to run this in the real world. So we want to replace that omnidirectional vision image with a real world image. And to be precise, the one that is collected by our fisheye camera that runs on the robot that we designed and constructed and runs in our lab. So given that we've trained all of the rest in simulation and we have a policy that works really well in simulation, the question that we're now asking is, well, how do we leverage all of our machine learning? Or how do we leverage as much as possible of our simulation-based policy and use that in our real-world scenario, but with the constraint that we're now inputting a real-world image and no longer the simulated image. So what we do is we say, well, we're going to try to create a correspondence between sim and real. And we're aware that there is actually quite a lot of research in this domain, trying to leverage some form of correspondence or trying to create an analogy between simulated images and real-world images. But the most common approach is actually taking a real-world image and synthesizing from that real-world image a simulated image, so something that looks similar and corresponds to what the policy would have seen in simulation. So instead of taking that approach, what we do is we say, well, what we're actually going to do is, or what we actually care about is the embedding that is input to our GNN. So that's the first part of our pipeline that comes from simulation. And so what we really want to do is we want to change the encoder. So we want the encoder to output an embedding that is as similar as possible to the embedding that our sim encoder would have produced for that same observation. And so what we do is we then minimize the loss between our two encoders, so the real encoder and the simulated encoder, with respect to the rest of our pipeline that is given to us and that is fixed from our simulated policy. And so we then train this additional, essentially, we call it our translator module with real-world images, and then introduce that translator into our pipeline and run the whole pipeline in the real world to perform real-world experiments using our sim policy. So this is our environment in action here, and I'm just going to play it through so you can see a couple of instantiations of what is going on. So you see a couple of different views here. So you see an overhead view, you see a lab view, and you see a view from the robot in the real world and what the simulated robot would have observed. And here you actually see the view from all the 5 sensors that are distributed in this environment. And you can see that 1 or even 2 of the sensors are able to see the target there. And eventually the robot is able to leverage that information and navigate to the target. So the target is kind of hidden in front of that big box in the front, but you see it navigating there. And you can see how this is very reactive. So we can pick up a target and the robot keeps on finding it. We can occlude the target and the robot learns how to leverage information from sensors and move around the obstacles. So it's a very adaptive setup because the sensor network is just simply reacting to what it sees and communicating that information in real time to the robot. So there's something else that is really cool about this setup that I just want to point out to you in this next quick movie. So obviously, it only really works if somebody can see the target, right? So if at least one of the sensors is in line of sight to the target, then this information will percolate through the network, and no matter where the robot is, it'll get this information from the sensor network, and it will be able to find a relatively high quality path to the target. But what happens if the robot can't see the target? Well, we did this little experiment just to demonstrate that everything is really reactive and the sensors are actually not positioned in any way. So you saw at the beginning of that movie, the robot was kind of hesitating. It doesn't know where it should go because nobody can see the target. But as soon as we pick up one of the sensor nodes and we place it in line of sight to the target, the robot starts moving in the direction of the target and actually eventually reaches it. So that kind of demonstrates this kind of plug and play aspect of this visual sensor network and that we came up with. And I find that kind of cool. This is just showing a couple of data points from evaluating this particular aspect of simulation. So you can see how when none of the sensor nodes, so the sensor nodes are in blue, when none of them are in line of sight to the target, the robot kind of does something erratic, is not able to find the target. But as soon as we put one of the sensor nodes in line of sight to the target, the robot succeeds in navigating to the target along a relatively efficient path. And so quantitatively, what else can we say about the system? Well, we've been able to say two relatively intuitive things. So if you increase the communication range amongst sensors and robots, the performance tends to improve. So our SPL, which is metric, which is success weighted by path length, approximates 1, and 1 is the optimal. And what happens when we add more sensors? So we densify the sensor network, and also in that case, we see an improvement of performance. So these are both very intuitive conclusions. We also compare our system to a naive baseline. So what happens if we don't have any communication amongst robot and sensors? Well, the robot just has to end up exploring the environment and finding the target by chance. And we saw that in those cases, we achieve at least a 2x improvement in terms of SPL. So this kind of concludes that project, and it also concludes a lot of things that I wanted to talk to you about. I just want to say a few more things and kind of lay out a couple of take-home messages. So I hope with this talk that I've convinced you that graph neural networks are actually a very elegant and reasonable architecture to use in multi-agent and multi-robot systems. They have a very simple way of allowing us to synthesize local policies. And these policies are learned in a way that they provide us very nice scalability as we start running them for very large systems. And we've also started verifying that the policies that we train in simulation transfer pretty nicely and gracefully to real-world scenarios where we lose a lot of the kind of idealistic characteristics that we typically have in simulation. There are a couple of things I'm excited about that we've just kind of started working on and that I'd also like to highlight here. So we're really excited about systems where the different robots are no longer the same, but they're heterogeneous. And we've really been looking into what are the advantages of running or learning heterogeneous policies. And this paper that we're presenting at AMAS this year really goes into that. We're also looking into environment optimization. So thinking about, well, what is it that we can do in the environment that helps agents devise better policies instead of just putting all the pressure on learning better policies. And finally, we're also really interested in thinking about, well, our robots are learning these uninterpretable policies. They're communicating with one another, but we don't really have introspection to what is going on between the robots. And so we're interested in devising methods that allow us to interpret these messages and understand the robot coordination in real time as a function of intercepted comms, essentially. So with that, I'd like to just thank my whole team. A lot of the folks that I'm depicting here have contributed to the works I've described today. I'd also like to thank reviewers and supporters and funders for their support in all of this. And with that, thanks a lot for your attention, and I'd be more than happy to take any questions.
Thanks, Amanda. It's been a pleasure having you. So at this point, I have a few questions that I'll ask myself. Then we'll also be able to take questions from the audience and from YouTube, and I will take those from there. And if I miss anything, Sunshine might help filter. So to start off, I want to go back to like way at the beginning of the talk. You showed a video of a flock of birds. And I know you've published on flocking before, but you weren't talking about flocking today.
Right.
And like flocking works tend to be very much on the control side.
Mhm.
And I wonder like how that's inspiring you now and how that might have evolved.
So what element of flocking? So flocking in general,
Yeah.
if flocking is inspirational to us, okay.
Or just like cooperative behaviors and intelligence.
Okay. So I think a couple of things that flocking is trying to teach us, or flocking in nature is trying to teach us, which we perhaps haven't fully been able to introduce into our algorithms gracefully yet, is a notion of resilience. So resilience to any type of disruption. So the addition and removal of individual agents, coalescing, distributing, separating when flocks of agents are encounter unexpected obstacles. A robustness in the sense that agents are, so you rarely have failure in a single, from both single and multi-robot or multi-agent perspective in flocks of birds, as in the flocks usually get where they want to get, and they rarely lose any individuals. And they're incredibly agile in terms of how near and how far the individuals can fly from each other. So I think all of these attributes together are things that we haven't really quite figured out yet. So we still are grappling with paradigms that when we use them, we have to introduce a lot of constraints. A very simple example is when you fly quadrotors, you can't fly them close. You can't fly them too far either. So we're still dealing with a couple of very simple, I think, it could almost be bi-directional, so like one-on-one type challenges that I feel nature has figured out, and we're still not quite there yet, let alone from a whole swarm perspective. I think that's maybe just scratching the surface of your question, but hopefully answers it at least partially.
Okay, thank you. I'm going to turn it over to Zoom real quick, but also I think we're nearing the hour, and typically we'll let it go over a few minutes, especially since like we often start a few minutes late. So if you're free, we'll probably go to 12:05 or 12:07 at least. Anyway, so Claude had a question about, I think, one of the ablation studies. Claude, if you're there, I'm going to let you unmute.
Can you hear me?
Yeah.
Yeah. Okay. So my question was, when you conducted the ablation study, I was wondering why it wasn't all done on the PC version, like the asynchronous, like the bigger model, where you would just limit the message passing between the thread, right? The bandwidth, the latency. Was there, or even the RAM and the flops? Like, what was the reason for like going more into the physical side of it?
Yeah, it's a valid question. So we could definitely have done that. I think the argument there is that whatever we introduce in simulation, it's procedurally generated. So the noise or the delays, it would be procedurally generated according to some inductive bias that we have about what we think we should be introducing in terms of noise, right? So definitely it could have been an intermediary step, actually. So adding another layer into our kind of ablation analysis. And it might have, I think there's no reason why we shouldn't have done it, but I don't think we should not have done what we did do, which is test the actual noise and the actual kind of asynchronicity in the real world. We don't know what it is, right? Because it's difficult to measure this, or in some cases you could profile it and monitor it, but we didn't want to make any assumptions about what it might be in a truly ad hoc setting, and what kinds of things that we should be, kind of running our systems on. And to be honest, we tested our physical ablation is simple in the sense that yes, we're running an ad hoc network, but it's, even though it's ad hoc, it's almost fully connected at all times because our lab is relatively small in this sense. So I think it really gets interesting when we start moving outdoors. And this is definitely one of the things that we're currently endeavoring to do. And you actually start seeing like proper effects from ad hoc, contention and bandwidth issues and delays and all of that all comes in. And those kinds of things are actually really, really hard to simulate.
Thank you. Thank you.
Okay, so first, I encourage the audience to ask questions either on YouTube, on the meeting chat, or on using the Q&A feature. At this point, I think I'll ask another question that I had. So this goes both to the multi-agent pathfinding and the sensor network scenario. I want to know a little more about like what information the robots were sharing and what they had available. So like, did they know about like the environment structure, and then like they were communicating to learn about like other robots and their locations and their intents? Are they just communicating the intentions? Like what's
so
this
in the sensor network example,
in both, like what information was
Yeah.
available to all robots, and then what information did they have to communicate?
So in the sensor network, the visual navigation one, no information about the environment was given at all. So they don't have a map, they have nothing. The only thing they have is a visual input of given through the omnidirectional camera. So that's this one here. Let me actually go back a few. Oops. You can scroll back.
Yeah, so I guess
So
I want to
here,
hear more about the path planning in a second. But one thing that surprised me about one of those videos was the robot didn't like, I was kind of expecting the robot to move toward the cameras and kind of follow the connectivity between all of the fields of view. But in one of those videos, it goes around the obstacle and kind of to a location that I think was out of the field of view of most of the cameras.
Oh, yeah, interesting. So yeah. So good catch. I will have to look through my videos again and see the same
It may have been just
artifact.
my interpretation of the video, but it confused me a little bit.
It totally might be. So the robots here, they didn't, so the policy that the robot learns is, so there's no reason why it wouldn't do that, because what it has learned from simulation is to follow a direction that ideally is as close as possible to the optimal path to the target. So that's what the sensors are training, are being trained for. So all of the nodes here, in terms of information, all of the nodes, they are observing the same thing, and that's that omnidirectional input. And they have learned to process that omnidirectional input to output a feature vector and embedding that is then communicate to one another and is conducive to the downstream task, which is I have to decide which direction to go in that leads me in a direction that is as close as possible to straight line path to the target. And in no way has the robot been trained. So the experts that we use in the imitation learning loss, in no way does anything with respect to node connectivity or anything feature in there. So the robot would not know. So that's why it wouldn't do that.
I guess one other question I could ask is, did you run into any other interesting failure points for that system? Like you showed one example where none of the cameras could see the object, but were there others?
So if none of the camera sees the object, the robot can't go to the object because nobody knows where the object is. That makes sense. So it's a failure, but it's a failure by design. I guess you could have additional failure where if you have limited, so you have to have communication coverage. So the robot has to be talking to at least one sensor. If you have very, very large environments, one potential failure you could have, and definitely we acknowledge this, is the environment could the robot could start moving out of the communication range of sensors, and it wouldn't know when it leaves the communication range. And once it's left it, there's no way of finding itself back, apart from random exploration. So that would be a bad failure, because it would then lose a lot of time trying to get back in. And there's no way
that's
we can.
That you would see more in field testing or larger environments.
Yeah, definitely.
Less likely in like the lab.
Yeah, for sure. For sure. Any kind of like environments that aren't limited, but it could definitely happen. And this is something one would surely have to implement an additional kind of, some shielding mechanism or connectivity maintenance mechanism on top to avoid it. But this can be done, but we would have to think of doing it.
So I could either ask another question now, or maybe you want to talk about the navigation side of the question, the path planning and navigation.
Whatever you want.
I'll go over to Sungjin had a question.
Mhm.
Sungjin, you can unmute yourself.
Sure. Yeah, I have a question on the sim to real gap on your work. And in general, what are the biggest challenges you have when you're trying to bridge the gap between sim and real? And also, does the gap between simulation and real world increases as the number of robots increase, or the environment
Interesting.
changes and so on? Like, what are the some other factors that make?
Yeah, so I'll answer it first from a communications perspective, because that's what we started studying first. So from a communications perspective, so sim to real is basically characterized by a distribution shift. And when you're training your systems in simulation, the kind of distribution we're looking at here is how is comms happening, right? So what are the patterns within which you receive and process communications? And so in simulation, how it's done is simulation progresses in lockstep, right? So every, delta t, you receive all the messages simultaneously from all your neighbors that are within a perfect communication range, right? And so here is actually a very good example of what is very different in the real world. In the real world, you'll never receive all the messages from your neighbors at exactly the same moment. They will come in distributed across a certain time window, right? So you're looking at a completely different distribution of how the messages are. And this here already is one example of what, how the distributions look different, right? So this is something we need to consider, but also in the real world, then you might not be receiving a message from a neighbor, although it is there, right? So that's another part that would contribute to the distribution shift between what sim would be telling you and what the policy has seen in simulation to what it's suddenly encountering in the real world. So those are kind of the aspects that we're most concerned about in terms of comms. As we move to kind of more the perception side of things, so the visual navigation one, there we were more concerned with the sim to real gap in the omnidirectional camera, so the visual input, because that was very different, and everything that the robots did was based on what visually was being seen. And so this then kind of then related much more to the sim to real types of challenges that people have been discussing in the classical sim to real literature with respect to the methods that you can use to close that gap from a perspective, from a perception perspective. So, yeah.
Okay, thank you.
So, Amanda, I don't see any new questions right now in the chat, and we're a few minutes over, so I think maybe this might be a good time to wrap up. So I was wondering if maybe you had any last things you wanted to say or share before the end of the talk, or?
No, I'm good. Thank you very much for having me.
Well, thanks a bunch, Amanda. It's been a joy listening to your talk today and speaking with you. So I guess with that, let's wrap it all up.
Thank you very much. Thanks, Mika. Bye.
Thanks. Goodbye.